Okay, Bismillah ar-Rahman ar-Rahim. Alhamdulillah, salatu salam ala Rasulullah. Today we're going to continue chapter 3. We stopped at this example. Okay. What do we have here? We have a single mass, a single spring, single degree of freedom system with a mass and spring only. Okay. What we're looking for, in this example, he said find the derive the equation of motion, and before that, in this example, find the free body. First of all, draw the free body diagram in order to derive the equation of motion. Okay, assume it's a free vibration. What does it mean, free vibration? No external force. Okay, and also assume x, the displacement x, is measured from equilibrium position. What does that mean? I'll show you in a minute what does that mean. Okay. Also assume, this is number one, the assumption. Also assume, given initial condition x at 0 equal x naught and x dot, the velocity, the initial velocity is v naught. Okay. Okay. Let me erase this. V naught. Okay, this is given, okay? This is the assumption given in the problem. All right, now let's start with the free body diagram. How are we going to draw the free body diagram? We start with the mass, show the mass clearly, just like your model. This is your mass. Okay, displacement. This is my displacement. X, the degree of freedom. Okay, X similar to X, mass similar to the mass. Now show the forces acting on the body. We have only one force, reaction force from the spring, and it's always against the motion. How much this force? It is K times the displacement X. Now, one student may say, where is the gravity or the weight of the mass? Where is the weight? Do we show the weight of the mass here? Remember in the last lecture? Remember the equilibrium position? Where is the weight of the mass here? Why we do not show the weight of the mass? It was cancelled. It was cancelled with what? The weight was cancelled with the static deflection. So the weight has nothing to do with the equation of motion if x is measured around the static equilibrium position. So whenever you see this statement, okay, whenever you see this statement, this assumption, x is measured or the degree of freedom is measured from equilibrium position, what comes to your mind? The weight of the mass has nothing to do with the free body diagram, and it will not be shown or it will not affect the equation of motion. All right, as simple as that. خلاص يا شباب. So this is, by the way, in most of the problems, in fact, in all problems that you see in the field, x is measured around equilibrium position. Like your car, for example. Your car now on the floor, already on the street, right? It's on static equilibrium position. The suspension system on static equilibrium position. Your engine, your pump in the field, always it's on static equilibrium position. Any vibrations, any displacement around the new position is your static equilibrium position. That's why we always assume in the problems that we are measuring from equilibrium position. Okay? All right, so this is your free body diagram. Done. Next, equation of motion. How are we going to find the equation of motion? Summation of forces. This is Newton's second law. Equal mass times acceleration. Where is the positive direction of force? Is it up or down? It depends. Depends on what? Depends on x, the displacement. X is going down, so this will go down. Okay. Now show what are the reaction forces we have here. We have only one force, which is against the motion. Kx equal mass times the acceleration of the displacement, which is x double dot. Okay. All right, if you rearrange, this is going to be your equation of motion. Okay. Okay, get some errors with the windows. That's normal. Okay, this is the equation of motion. Okay. This is the equation of motion. This is your equation of motion. Okay, خلاص. Now from this point, can you solve? Can you get the solution of this system? Yes, from this point and on, this is chapter 2, Laplace transform. You're going to use Laplace transform. So you need the initial conditions, which are given here from the problem, and you need to solve. Take the Laplace transform, okay, substituting the initial conditions, solve for capital XS. Then what we call this step from here to here, we call it partial fraction expansion. Remember, chapter 2? Okay, now what I'm going to do here, from this step to this step, I'm going to do one small step, which I'm going to divide the numerator and denominator by m. I'm going to divide the numerator and denominator by m. Is that okay? Divide by m. So here you will have k by m. You will have k by m. Why I'm doing this? Because I'm going to define a new definition. This k by m, I'm going to give it a new name. Okay. I don't know why the pen is giving many errors. That's normal. Okay, this is a new name. I'm going to give it to k by m from now on, and it's going to be omega n or omega n equal square root k over m. And this is we're gonna call it, we will give it a name. We will call it natural frequency. We call it natural frequency. Why we call it natural frequency? In the second slide, okay, I will show you why we call it natural frequency. But from now on, ya shabab, I need you to remember this from now on until the end of the semester. Okay, we're gonna need this definition: omega n equals square root k over n. Okay, so we divided the numerator and denominator by m. So this k by m, I will call it omega n squared. Okay, omega n squared, same. Okay. Now continue the partial fraction expansion, then go to the table and get the inverse Laplace. The inverse Laplace of this will be cosine omega n, okay, which is given here. And the Laplace transform of this also sine omega n. Okay? And this is your solution. This is your solution. This is the solution we got. Or, remember in chapter 2, how you can go from cosine and sine to one cosine with the common amplitude and phase angle. Similar to complex numbers, if you remember complex numbers, how to go from here to here. This common amplitude will be square root of the magnitude of cosine squared plus the magnitude of sine squared, just like here. Okay, this is for R, the amplitude. And this phase angle, we call it phase angle tan inverse, the imaginary, where is the, or the sine, V naught over omega n over the magnitude of cosine, okay? So this is for psi, okay? All right. Why are we doing this? Why are we doing this? Because it's much easier to draw. Can you draw? Yes. This is the time. This is x of t. It will be what? It will be harmonic motion, right? It will be harmonic motion. Like what? Like cosine. Like cosine. Okay. So if you draw it, cosine, similar to this one. Let me try. So it's lagging. Okay, minus psi, so it's lagging. Similar. Let me draw it from here. It's the same concept. Same concept. So you say it will be cosine, for example. Okay, and this is the phase. And this one is the this one is what? The amplitude, which is R. This is the phase. Okay. The psi here, it's negative, right? So it's going to be on the other side, lagging. Okay, this is just for demonstration, for understanding, okay? And this one from here to here, What we call it? We call it the period. Do we know the period? Yes, the period is what? The period is 1 over the frequency. Remember in physics, frequency in hertz. Okay, hertz was, remember, omega from now on, ya shabab, whenever you see omega, the frequency omega, it's in radian per second. Okay, this is the default. So to go from here to here, it's going to be 1 over. Hertz means what? Hertz means cycles per second. This one radian per second. Okay, so how to go from cycle per second to radian? It's going to be omega n over 2 pi. So the period will be what? 2 pi over omega n. So this is radian per second. Okay, so you can take the second to the top, it will be the same unit. Okay, all right. So this is the frequency. Omega n is the frequency of this harmonic motion. Okay, the frequency of the harmonic motion given from the solution omega n. And the period also you can measure it or calculate it from omega n. Okay, now we know the period. خلاص. All right. So how can you describe this? This is simple harmonic motion. This is my solution, simple harmonic motion. Now we defined a new frequency. We call it a natural frequency. Square root over k over m. We're going to memorize this. We're going to keep it in your heart. Okay, do not forget it. Okay, this natural frequency now, why we call it natural? Remember I said we're going to call it natural, and I will explain later. Why we call it natural frequency? First of all, you know it's the frequency of the motion. But why we call it natural? I will tell you why. Look, if you change the initial condition, keep the same system. The system is the same. Mass the same. K is the same. Okay? I did not change the system. I changed the initial condition. So instead of giving here x naught, I will give it 2x. For example, instead of pulling the mass 1 centimeter, I will pull it 2 centimeter down, okay? And release. What will happen? It will vibrate, right? It will vibrate. But what will be the solution? What will be the solution? You will follow the same procedure here, right? Follow the same procedure. And look at the solution here. This is the final. What will change if you change only x naught and v naught? What will change? Only what, ya shabab? Only the amplitude. See, the amplitude depends on what? On the initial conditions. Okay? What about the frequency? The frequency, look at the frequency. Where is the frequency? Frequency k over m. Does it depend on the initial conditions? No. So the frequency will not change. Omega n will not change. Right? As a result, the period will not change. What will change only if you change the initial condition? What will change only? What will change is the amplitude only. So if you change the initial condition, what will change? The amplitude may increase if you increase the initial conditions, right? So here it will be the same, right? The period and the frequency will be the same. So what will change only? Only the amplitude. Also, the phase angle, is it gonna change if you change the input? Yes, the phase angle will change. This one depends on x naught and v naught. So the angle here, the phase, may also change. Okay, you will have different size. So this is psi 1, this is psi 2. Okay, and here you have R1. This is a new one, R2. خلاص يا شباب. What about the natural frequency? Natural frequency, same. It will not change. Okay. Now what if you change again the initial conditions? X naught, 3x naught, V naught, 3V naught. Is the natural frequency will change? No. What will change only? The amplitude and the phase angle. The natural frequency or the frequency of the oscillation will be always the same. That's why we call it what? That's why we call it natural frequency. Natural frequency, okay, will not change unless you change system parameters. K, and M. See? All right. If you change the initial conditions, it will not change. Okay. Natural frequency determined only by system parameter, not the initial conditions. خلاص يا شباب. That's why we call it natural frequency. That's why we call it natural frequency. Easy way to find the natural frequency. Easy way to find natural frequency. The natural frequency, there are two easy ways. Either from the beginning, from the equation of motion. This is the equation of motion. Okay. This is the equation of motion. Let me use another pen. From the equation of motion, okay, here, mx, okay. Let me use a easy way to find the natural. Go to the equation of motion, mx double dot plus kx equal to 0. Okay, this is your equation of motion. If you divide by m, the whole equation, if you divide by m, what will happen? It will be x dot plus k over m times x equal to 0. Or what is this? Did you see this before, Shabab? Yes, this is what? This is the natural frequency squared. Okay. And by the way, this is your equation of motion in standard form. Standard form. This is the equation of motion in the standard form. When you divide the equation by m, why we call it standard form, or why we like to see the equation of motion in standard form? Because here, from here, you can easily pick up or measure the natural frequency. By the way, the natural frequency is like your temperature when you go to the clinic to see the doctor. How he will see if you are sick or not? By first measuring your temperature, right? Natural frequency is the same as the temperature for your body for mechanical systems. Whenever we want to see how healthy your mechanical system, we measure the natural frequency. Whenever we want to control it, okay, we want to design a controller, okay, we want to analyze it, we measure the natural frequency, okay. We will talk about it later, inshallah, when we come to chapter 8 and 9, the analysis of the time domain and the frequency domain analysis, okay, of dynamic systems. Okay, so this is number one, method number one, how easy way. Method number two, just like in the lab this week, you will see, you will give your system initial conditions, then you will measure the response on a piece of paper, just like you did in the lab. Then you measure, this is the time, this is x of t. So we call this the time response. Measure t, what's t? And from t, you will get the natural frequency, 2 pi over natural frequency. And then you can calculate. As simple as that. Okay? So this is, you can do it experimentally, and this is, you can do it mathematically. All right? Or analytically. Okay, so this is the first example, the easy example. I try to be very slow here in order to comprehend the concept. Okay, I hope I was clear. Let's go to the second example, or the other example. Similar to the first example, all we did here, we added what? We added a damper to the system. We added a damper to the system. We're looking for the same thing. We're looking for the free body diagram, draw the free body diagram in order to derive the equation of motion. Assumption, same assumption as before. Okay, x is measured from equilibrium position. And by the way, in the problems that you will see in the book or in the exam, always it should be clear, ya shabab, the displacement is measured from equilibrium position. He should say that clearly. Okay, all right. Also given initial condition x naught and v naught, the initial conditions. Okay, the initial displacement and the initial velocity. All right. So how are we going to do this? The free body diagram. We will start with the model. Show the model. Start with the mass. This is my mass. This is my displacement, similar to the model. Now show the reaction forces. We have one reaction force here from the damper, and we have one reaction force here from the spring. Spring force is Kx, damper force Cx dot, remember? By the way, C usually they use in vibrations, mechanical vibrations books, or vibration guys, they like to use C for the damping coefficient. In control, like in your book, they like to use B. Okay, so B or C, they are the same. Okay, same meaning. It's damping coefficient. Okay, usually is giving. It's a number. It's a constant. All right. Now, how are you going to solve? First, let's get the equation of motion. Summation forces equal mass times acceleration. Where is my positive direction of force? Down. Down. So we have two reaction forces minus Cx dot minus Kx equal to mx double dot. Okay, rearrange, and you will get your equation of motion. This is your equation of motion. Okay, equation of motion. Oops. Okay. We have to be very patient when we write here. خلاص, we got it. Okay. All right. So this is the equation of motion. We got the free body diagram. This is your free body diagram. And this is the equation of motion. خلاص يا شباب. Good. Now we want to solve, get the solution. Okay. Also solve for x of t. Get the solution. All right. Now what I'm going to do here, one more thing. I will divide the whole equation of motion by m. Why I'm doing this? To write the equation of motion in the standard form. So this is the same equation of motion. When we divide by m, we will get the same equation of motion, but we call it in standard form. Why we write it in the standard form? Remember, Aisha, when we write it in the standard, you will see omega n squared here, natural frequency, you will get it. And also, we will learn and get introduced to a new, very important variable, very important constant. We call it zeta. And this zeta is the damping ratio. So from now on, whenever you see zeta, it is equal to C over C critical. What is C? C is the damping ratio. What is C critical? C critical is 2 square root Km. The stiffness times the mass. Okay. Now, how did I know this? Okay. Is there a proof? Yes, I will show you. Let's start from here. Let's start from this definition. I will show you the proof. Okay. How did I come up with this equation? Start from here. 2 zeta omega n equal to 2. What did we define C? C over C critical, which is 2 square root Km times omega m. What is omega m? Square root K over m, right? Oops. Let me use a new slide, maybe it's better. ولا خلاص, maybe, because it's not really important, just a proof for understanding. Let me write here, this is m. We have very small space here. Okay, oops. This is m. I hope it's clear. M. Let me write it here again. 2c over 2 square root km times square root k over m. Now much more clear. So this 2 will cancel with 2. K will cancel with k. Okay, and what left? Left c on the top. And in the bottom we have square root m times square root of m. So it is the same. Is it the same? Look. Yes, same. Okay, it is the same. Okay, so it's a proven. خلاص يا شباب. It's a proven. This is what you need to remember, okay? This is what you need to remember. Damping coefficient. Or sorry, damping ratio. Why we call it damping ratio? Because it's the ratio of your actual damping of the design of the system, of your damper, to the critical damping. What is the critical damping? It's a constant. For any system, it's a constant. 2 square root K times M. We call it damping coefficient, critical damping. Okay, critical damping. This is a threshold that it will make sense, inshallah, later when we come to the analysis. Okay, the barrier or the it's a point between two cases that we will use in the analysis later, inshallah, when we come to chapter 8. Okay, now let's continue the solution. So this is in the standard form. You need to memorize this, inshallah, how to write your equation of motion in the standard form. Now solve it, take Laplace transform, solve for xs, partial fraction expansion. Now remember, when we have a quadratic equation in the denominator in chapter 2, what you're going to do next, you have to check your solution or your roots. Either you will have 2 real roots or 2 identical real roots or 2 complex conjugates. Okay, now for this problem, assume also, the assumption, also assume, I forgot to tell you, assume zeta is between 0 and 1. Why I'm assuming this? Because this is very special and popular case. When zeta between 0 and 1 here, when you solve for the roots, you will have 2 complex conjugates. So if you have 2 complex conjugates, what is the next step? You need to complete the square. Remember, Shabab, chapter 2, you need to complete the square. Complete the square. If you complete the square, why we complete the square? Because it's easily for you. You can go to the table and get the inverse Laplace. Now, before we get the inverse Laplace, let me define a new definition for this omega n square minus zeta square omega n square. I will give it a new definition. I will call it omega d square, or omega d square equal to square root omega n. Oops, sorry. Let me erase this. Omega d equal to omega n square root 1 minus zeta square. Okay, this omega d we're going to give it a name, ya shabab, okay, and we will memorize it. This omega d, we will give it a name. Okay, you have to be very patient. This omega d is what we will call it damped natural frequency. This omega d, damped natural frequency. Okay, let's keep it in our mind. Okay, omega d equal to omega n square root 1 minus. How did I get this? From here, from this part, I will give it a name. This constant, it's constant, right? Omega d equal to omega n square minus zeta square plus or times omega n square. Let's keep it in our mind. So instead of using all this, I will use only here omega d squared. Okay, now expand. You will have 2 parts here, expand it. Then go to the table and get the inverse. If you go to the table, you will see clearly that this is what? This is cosine multiplied by decaying exponential. This is my solution, and this is the inverse Laplace. The inverse Laplace will be decaying exponential for this one times cosine, and this one decaying exponential times sine. We have cosine, we have sine, we can write it in common with common amplitude and with common what? Psi. Remember how to get to the r? R is square root of what? This magnitude square plus this magnitude square. What about psi? Psi is tan inverse of this magnitude or amplitude divided by the magnitude of cosine. As simple as that. خلاص يا شباب? How to get r and psi, just like you did here. R, this amplitude square plus this amplitude square, take the square root for all. Psi, this magnitude, tan inverse of this magnitude over this magnitude. Same thing you can do here. خلاص يا شباب? I assume you know how to do it. So this is my solution. Okay. Can you draw the solution? Yes, we can. just like we did in the previous example. This is the time, this is x of t. What will be the difference between this solution and the solution before? Here we have decaying exponential. So not just it's harmonic, but decaying. So you will start, this is cosine, so let's assume we're starting from here. You will have same harmonic motion, but what will happen to the magnitude? It will get less and less and less. Okay? How do we know about this envelope? This envelope will be what? Of the decaying, or the decay. This envelope is r e to the power minus zeta omega n t. This part. Okay? This one. What about this one? Do you know the phase? The phase is psi. Do you know the maximum magnitude or amplitude? Yes, it will be r. What about the period? Can you know the period in order to draw? How are you going to draw without knowing the period? We know the period. The period is equal to what? 2 pi over the frequency of the oscillation. Do you know the frequency of the oscillation? One would say, yes, we got it from here. This is the frequency of the oscillation. Right? The same frequency. Omega d. Frequency of the oscillation is omega d. So it's going to be omega 2 pi over omega d. Do we know what's omega d? Yes, we defined it from before يا شباب. What is omega d? Omega d خلاص لازم نحفظها يا شباب. This is the natural frequency square root 1 minus zeta square. How did we come up with this definition? From here. This is the definition that we come up with. Okay? And we call it what? Damped natural frequency. Okay? First of all, why we call it frequency? Because this is the frequency of the oscillation. Now, why we call it damped natural frequency? Why we call it natural frequency again? Why we come up with this word, natural? Again, because if you change the initial conditions, if you do not change the system, you do not change the system parameter, C, K, or M, just change the initial conditions. Do you think the frequency will change of the oscillation? No, the frequency will not change. Why? Because the frequency depends only on natural frequency, which is depending on K and M, and depends only on the zeta, which is also depends on C, K, and M. It does not depend on the initial conditions. What will change only if you change the initial condition? What will change only? The magnitude or the amplitude of the oscillation and the psi, the phase angle, that's all. But the frequency or the period will be exactly the same. You got it? That's why we call it natural frequency. And we give it a name damped here. Why we give it name a damped? Because it's different from the natural frequency for undamped system. This is for undamped system that we got it from here. Okay? From this oscillation. This is the frequency for damped system. It's different. Okay? But it depends on the natural frequency, by the way. Okay? Remember, we assumed here under damped condition. We call it under damped because zeta is less than 1. The damping coefficient is less than critical damping. That's why we call it under damped conditions. We will talk more about this analysis, inshallah, later in chapter 8. Also note that omega d always less than omega n. How do I know this? Mathematically. Omega d always a partial of omega n because zeta, okay, usually it's less than 1. So omega d always less than omega n. Okay? All right? So this is the conclusion, okay, of today's lecture. We saw 2 examples, single degree of freedom system, one with the spring and one with the spring and damper. Free vibration. Why we call this free vibration? Because we have no external force, only initial conditions. So, and we call this, by the way, a homogeneous equation, differential equation in math. Here we call it free vibration, because we only give it initial conditions. So I hope this is clear. One more concept that we're going to use in chapter 8, inshallah, when we come to the analysis of dynamic systems. Okay, look at this solution, x of s, from here. This one, I got it from here. Where is it? This one, x of s. Look at the denominator. Okay, look at this equation, the quadratic equation. The roots of this denominator, what we call it in math, ya shabab? If you remember in math, we call these roots what? These are the roots. These are the roots of characteristic equation. This one we call it what? This one we call it the characteristic equation. Okay, why we call it characteristics or characteristic equation? Because the roots of the characteristic equation will determine two very important things about the characteristics of the transient response or the time response or the solution. Okay, if you have two complex conjugates, okay, the real part will determines the stability of the system, and the real part only determines the frequency of the system. Stability is very important concept in dynamic systems, in control, in vibration, in all engineering. In real life, we always design our systems for stability. We want to have a stable system. So the real part must be always negative for stable. Okay, negative means what? Stable system. Negative means stable. Okay, positive means unstable system. What does it mean, stable system? Like here, in this solution, when you are converging, when your system is converging to a certain value, and it will stop there, we call this stable. As simple as that. We will talk about it later, inshallah, in chapter 8, but for now, just for your understanding. So, converging means stable in math. Converging means stable. Diverging, when it starts from amplitude and it will get larger and larger, okay, we call it unstable. We will talk about stability later, okay? This is just brief talking, okay? Brief talking, okay? So these are the roots. And by the way, we call this, the roots, we call them in math what? We call them eigenvalues. Remember eigenvalues and eigenvectors? These are the same, the roots, okay, from math. Just for understanding, okay? To see the relationship between math and dynamic systems. Okay, one more thing before we close today's chapter. What if you have two springs in parallel? Is there an equivalent of these two? This will help you when you solve mechanical systems. The equivalent, simply, the equivalent for two springs in parallel, the equivalent is addition. How do I come with how did I come up with this conclusion? From the free body diagram. You will sum these points, you will add them together, so you will have here the equivalent here will be K1 plus K2, as simple as that. So the equivalent is K1 plus K2. So to simplify your problem in the homework or in the exam, instead of having this one, you can have one equivalent spring, and especially if you have complicated system, you can make it smaller, your problem, or the free body diagram smaller and shorter for derivation. So the equivalent here will be K1 plus K2. What if you have two springs in series? This is more complicated. Why? Because here we have degree of freedom here, by the way. This point, there is another degree of freedom, y. I will call it y. This one, x. Okay. So in order to see the equivalent between K1 and K2, you need to derive the equation of motion at y and x. You can do that at home, but it's not necessary now. Why? Because I did it already for you, and you do not have to prove it for me. There is an equivalent between them. What will be the equivalent? 1 over K equivalent will be 1 over K1 plus 1 over K2. Okay? All right. This is, by the way, similar but opposite to resistors in electrical systems. Okay? Remember, there is some concept similar but opposite. Okay? Opposite to electrical systems. Here, if you have two springs in series, the equivalent, 1 over K equivalent equal 1 over K1 plus 1 over K2. Here, if you have two springs in parallel, the equivalent will be K1 plus K2. خلاص يا شباب. This is what you really need to know for today's lecture. Can you find the equivalent damping for dampers in parallel or in series? It will be the same. Okay? Similar. Okay, similar to springs. Same, okay? Dampers, same, to springs. Okay? These are extra information for now. Okay, if you want to solve more complicated systems, you can read it at home. If you have any question, you can ask me. This is also just for your information. We did this in the lab. If you have a mechanical system and you're looking for the mass or the spring, either one of these you don't know. In the lab, we have unknown spring and we have a known mass. Here, the opposite. We have unknown mass, like a turbine. This is the turbine. And we have a known stiffness, like the stiffness of the shaft, rotor shaft. Can you find the mass of the turbine? Yes, from the equation of motion. Okay, we know the natural frequency is square root of k over j, or k over the mass. Here, because torsional motion, k stiffness, k torsional over the mass moment of inertia, which is equal to what? 2 pi over the period. So all you have to do, give it initial condition, then record. This is the time domain, and this is the theta of t. Give it initial condition, just like in the lab. In the lab, we have x. Here we have theta. So you will record the oscillation on a piece of paper using accelerometer. Then all you have to do, measure t, and from t, if you get t, you will get the natural frequency, and you will get k, because this is already you know. So either you don't know j or you don't know k, just like in the lab. One of them unknown, you can find by finding the natural frequency. That's all for today. Thank you for listening, and see you inshallah in the next class.